I want to start today with a little visualization challenge. If you're not driving, maybe close your eyes for a second and picture an electric motor. Just, the first image that pops into your head.
I'm going to go out on a limb here. You're picturing a cylinder, a can shape.
A can shape, exactly. Something like a soup can or a rolling pin.
That's the classic shape, the one we all know. It's been around forever.
It really has. But what if I told you that to make things like electric airplanes and high-performance drones a reality, engineers are taking that soup can and basically squashing it flat.
Like a pancake.
Literally a pancake. Today we're diving into axial flux motors, which the source material actually calls pancake motors.
And it sounds simple, going from a cylinder to a disc. But when you get into the research from Gireas, Krishnan, Parviainen, you see this isn't just about fitting it in a tight spot.
No, it changes everything, especially when you're fighting gravity.
Yeah.
And that's our mission for this deep dive. Why is this specific shape revolutionizing how we fly? We've got the incumbent, the radial flux motor, versus this challenger, the axial flux motor.
So to really get the why, we have to start with the what. The difference between radial and axial isn't just the outside shape. It's about how the magnetism,
Absolutely.
how it moves inside the machine.
Right. So let's stick with that soup can for a minute. The standard radial flux motor, or RFM, the sources say the copper windings run along the length of the shaft, right?
Correct. And the magnetic flux, that invisible force that actually creates the movement, it flows outward from the center, radially.
Like spokes on a bicycle wheel.
Exactly like spokes on a wheel. The action is happening on the walls of the can.
Okay, standard design. We get it. Now flip the script. The axial flux motor, the AFM.
The pancake. Instead of a cylinder, think of a disc. A dinner plate. The windings aren't running along the length anymore.
How are they arranged?
They're laid out flat, like slices of a pie on that plate.
And the magnetic flux. It's not going out like spokes anymore.
No, now it flows parallel to the shaft, axially. So you can imagine two magnetic plates trying to pull together, face to face.
Ah, okay. So that's the aha moment. We haven't changed the physics. It's still copper and magnets, but just by changing the orientation.
You change everything. The leverage, the weight, the entire package.
And that packaging brings us to the first big battleground. Weight. In the air, weight is the enemy. Always.
It is the enemy. Every single gram you save in the motor is another gram of battery, which means more range. And this is where the AFM starts to really pull ahead in the literature. The comparative studies all highlight this huge difference in what they call active weight.
Active weight. So that's just the parts that do the work, the iron and copper.
Exactly. In a traditional cylinder motor, to get more power, you usually need more heavy iron, what they call back iron, just to guide the magnetic field around. It's a long path.
So they're carrying around dead weight just to complete the magnetic circuit.
In a sense, yeah. It's structural overhead. But the AFM has a much shorter magnetic path. It just hops across the gap. The sources are really clear on this. For the same power, the axial flux motor needs way less iron.
Which means it's lighter.
Lighter and smaller. The power density is much higher. Because they're flat, you can tuck them into spaces a long cylinder just won't fit.
And this is where the aviation part really clicked for me. The sources talk about putting the motor directly inside the propeller hub.
Right. Think about aerodynamics. A big soup can motor sticking out from a wing creates a ton of drag.
It's like strapping a bucket to the wing.
It is. But a pancake motor, it's so thin you can hide it right behind the propeller. It streamlines the whole design. It gives aerospace engineers so much more freedom.
So it's lighter for more range and smaller for less drag. But there's another piece here that seemed even more important. The torque. The twisting power.
Ah, this is my favorite part. It's just basic leverage.
Okay, walk us through it. How does being flat give you more leverage? A motor's a motor, right?
Not quite. In that cylinder motor, the force is happening at a fixed distance from the center.
Okay, like a door handle that's always in the same spot.
Exactly. And torque is force times radius. So to get more torque, you need more electricity, more heat.
A bigger radius.
Yeah.
A longer lever.
You got it. And that's what the pancake shape gives you. As the disc gets bigger, the working parts, the magnets and coils, get further from the center. You're increasing the radius.
So just because of its shape, you get more twisting power for free.
Essentially, yes. You're not adding more energy. You're just applying the force in a much smarter place.
Which is perfect for turning a big propeller.
Mm-hmm.
It doesn't spin super fast, but it needs a lot of muscle to push the air.
Precisely. And this is a huge win because it lets you get rid of something heavy, complicated, and prone to failure.
The gearbox.
The gearbox. Gears are heavy, they need oil, they break. In a plane, you can't just pull over if your transmission fails.
No, that'd be bad.
Very bad. But because the AFM has so much natural torque, you can often go direct drive. The motor bolts right onto the prop. That's a massive win for reliability and weight.
A total game changer. And there was a secondary benefit to that shape, too, that the Jarrah's source pointed out. Cooling.
Oh, yeah. High power means high heat. No way around it. But a cylinder motor traps that heat inside. It's like wearing a winter coat for a marathon.
So you need liquid cooling, pumps, radiators, more weight.
Right. But the axial flux motor is often hollow in the middle, like a donut, and its flat faces have this huge surface area exposed to the air.
And on a plane, there's a propeller blasting air over it constantly.
So it's naturally self-cooling. It means you can run the motor harder for longer without it overheating. It's another reason they can get such high power density.
Okay, so it's lighter, has more torque, and it cools itself better. But flight is also about control, about agility, and that's where the sources bring up inertia.
This is absolutely critical for things like drones and quadcopters.
So inertia is just resistance to changing speed, right? How hard it is to get something spinning and then stop it again.
That's it. And a standard cylinder motor has a heavy, solid iron rotor. It has high inertia. It's a flywheel.
It wants to keep spinning.
Which is terrible for a drone. If a gust of wind hits your drone, the computer needs to change a propeller speed instantly to stay level. We're talking milliseconds.
With high inertia, the motor's sluggish. It fights the command.
And in that moment of hesitation, your drone has already flipped over. But the AFM can use much, much lighter rotors. Sometimes it's just a thin disc holding magnets. Some are even coreless with no iron at all.
So the rotating part is feather light.
Relatively, yes, which means low inertia. They can speed up and slow down incredibly fast. The sources mention missile fin actuators as an application.
Wow. Okay, that puts it in perspective.
Right. A missile fin needs to react instantly. That same agility is what keeps a drone stable in turbulence.
Okay. I am completely sold. It's lighter, stronger, cooler, faster. So here's the billion-dollar question. Why isn't every single motor a pancake motor? Why is there still a cylinder in my drill?
Ah, yes. The catch. There's always a catch. And there are a few big ones. The first one is that they are just really, really hard to build.
Manufacturing.
Specifically the stator, the part with the copper windings. On a radial motor, you just stamp out steel sheets like cookies and stack them. It's cheap, it's fast, we've perfected it.
But not for the axial motor.
No. The flux flows differently, so you can't just stack sheets. The source material talks about having to wind a ferromagnetic ribbon, almost like a roll of tape, to create the core. It's time-consuming and way more expensive.
So you'd pay for that in a plane, but not a desk fan.
Exactly. And then there's the unbalanced force issue.
That sounds bad.
It is. If you just have one spinning disk of magnets next to one stationary disk, the magnets want to violently clamp shut. There's a massive force trying to crush the motor.
And in a cylinder, those forces are all pointing outwards, so they cancel each other out.
Correct. But here it's a clamping force. The solution is to use a sandwich design. You put one rotor between two stators, or two rotors with one stator in the middle.
Like a magnet Oreo.
Exactly like a magnet Oreo. That balances the forces. But now you've just doubled your parts count. You've made the assembly much more complex.
It's not a better motor, it's a more complex system.
Precisely. And there was one more little nuance in the Parvianen thesis about pole count. It turns out the pancake isn't always the winner.
Really?
Yeah, it showed that radial flux motors are actually better if you only need a few magnetic poles for high-speed applications. The axial flux design really shines only when you have a high pole count.
Which means lower speed, but higher torque.
Exactly.
Which brings us right back to the propeller.
Right back to the propeller. The job it needs to do is perfectly matched to the sweet spot of the axial flux motor. It's like the technology was just waiting for electric aviation to come along.
So let's sum up the verdict for this guy. The radial motor isn't going anywhere for ground-based stuff, but for flight.
For flight, the AFM wins on every metric that matters. Power-to-weight ratio, high torque density to get rid of the gearbox, compact size to reduce drag, and that super fast response time for safety and stability.
It's really a case of form following function. The cylinder was for the industrial revolution on the ground. The disc is for the electric revolution in the air.
I think that's a perfect way to put it.
Before we sign off, there's one last thought from the sources that just blew my mind. We talked about removing the iron to save weight.
The coreless designs.
Right. Some of these motors eliminate the iron core entirely. It's just copper, magnets, and resin. And the efficiency numbers.
They're staggering.
The sources were quoting 97, even 98% efficiency.
Which is almost unheard of. That means almost no energy is being wasted as heat.
It just makes you wonder if you can remove the heavy iron skeleton of the motor entirely and just fly with the muscles, the copper and magnets, how much lighter and longer range could electric aircraft really get?
It's the ultimate goal, isn't it? A motor that is almost pure torque and zero dead weight. We're not there for jumbo jets yet, but the trajectory is pointing straight up.
A fascinating future, and a great reminder that sometimes the biggest leap forward comes from just flattening your perspective. Thanks for diving into the stack with us.
Anytime.
We'll catch you on the next Deep Dive.
Yeah.